before we go too far into rotational dynamics, we're going to need to understand the difference between a force diagram and a free body diagram. We're well acquainted with the force diagram already that we use for the particle model. Okay? And the particle model simply says that we can take object A, it's object A here, and we can treat object A as if it were a point mass. Okay, and so what we do is we treat object A as a point mass, in other words, a particle, and then we apply all the forces to that point. Okay, and so, for example, if we're pulling on it with a string, we have the pulling force. We go around our contour, we see wherever the contour touches another object, we have to replace that object with the forces applied by that object. And so when we get to the table, we have to put in the normal force exerted by the table and the friction force exerted by the table. The normal force, of course, is perpendicular to the surface, and the friction force is parallel to the surface. Then we look back and we say, are there any gravitational fields, any magnetic fields, and so on? And we say, well, okay, in this problem, we do have the gravitational field, and so the force of gravity by the Earth on the block A is going to be pulling down toward the center of the Earth. And so what we've done here is we've constructed what we've called in the past the force diagram for a particle. Now, it's not always that simple. For example, supposing we have a table and we have let's say a tall block, and here it might depend. The dynamics of what's going to happen, excuse me, is going to depend on where we apply the force. If we apply the force right along here, or below, or lower, the block might just slide like it did for block A. But if we apply the force somewhere up in here, for example, the block might tip. Okay, it might tip about a point here. We'll call that point P. So if the table has friction, it will tip about that point, and we have to understand now that the position of the force is very important. Okay, and for that reason now we draw what we call a free body diagram. What we're going to do is we're going to take the block B, excuse me, and we're going to free it from the table. We're going to take this block, we're going to pull it, and we're going to bring it down here to the left. Okay, and when we do that, we have the block free now, and so we have to now construct the forces exactly where they are, where they're acting relative to the block. Okay, and so if it's about the tip, about this point P right here, it's about the tip about that point, then we know that the normal force would be, oops, excuse me for a second here. This would be the normal force. The normal force would be the point where the table is in contact with the block, which would be at point P, because it's tipping about that point. And the friction force would be exerted along this direction here. Okay. And then the pulling force we can apply wherever we like. Oops. Again. Okay. So the pulling force could be applied at any point here. We'll just put it at some general point right there. Now, let's say we're going to make a problem now. We want to define this, we're going to do a no find. And I'm going to say, well, what I want to find is where exactly can I apply that force such that it will just barely begin to tip. In other words, what is the maximum distance that I can have? That's D1, sorry. What is the maximum distance that I can have between the pivot point and the line of action of the pulling force such that it will just start to tip over? Okay? And so we can see that the line of action is going to be parallel to the floor. The force is going to go in this direction. And so the line of action, we're going to call it D1. And that's the thing we're trying to find over here. So we're trying to find that We assume we know the pulling force, we know the thickness of the block. We know that the gravitational force right here is going to act right through the center of the block. Okay, and so we know that let's say we know this is D2. Okay, actually, the gravitational force acts on all the particles in the block, but we'll be able to derive later on that we can treat it as if the gravitational force was being applied right at the center of mass of the block. Okay, and in a different video, I'll explain what the center of mass is. But for now, we can consider it to be the point where all the mass is concentrated. Okay, so assuming we know that point, and we can apply the normal force, which is acting at point B, only point in contact with the floor right now, we can solve this problem. So let's supposing we know the coefficient of friction, we know the mass, we know the gravitational force, and we want to solve for this force D1, or the distance to the line of action of the force P, such that the block will just be the tip. Okay, we'll apply the conditions of static equilibrium. And we know already that the condition of static equilibrium for force is that if we add up all the forces on an object, they have to add up to 0. What we haven't learned yet, and we're going to learn it right this second, is that if we add up all of the torques on an object, again, that's a vector, they also have to add up to be 0. Okay, so right here are the conditions of static equilibrium. Conditions of static equilibrium for a rigid body. Okay, so let's put it in practice. Okay. So we'll take a look at the forces first, and we'll break those up into x components and y components. So we know that the sum of all the forces in both directions have to be 0. Okay, we'll do that first. That's easy, because we've done it so much. Okay, so we know the pulling force is in the positive direction, and we know the friction force is in the negative direction because it's pointing to the left. And those are the only two forces in the x direction, so they have to go to 0. So let's apply the friction model, which says that the friction force is equal to our coefficient of friction times the normal force, and we get 0. Okay, we have to add up to 0. Now we'll look in the y direction, and we'll see in the positive direction we have our normal force, it's acting straight up. We have our gravitational force, which is acting straight down. Those are the only two forces. They have to add up to 0. Okay, so we can now figure out what our normal force is because we can use our model for the gravitational force. The gravitational force is equal to mg. And so now we've calculated the normal force. Putting that back into this equation here, we can now see that the pulling force is going to be equal to mu times the normal force, which we now show as mg. Okay, so now we have an expression for the pulling force that will just posit the tip about point P, assuming that we know the coefficient of friction. Okay, so actually we didn't have to know this in advance, we just calculated it. Now the third condition of equilibrium that we're not so familiar with is that the sum of all the torques have to add up to 0. And in this case, all the torques are pointing either clockwise or counterclockwise, which means we'll talk about the vector nature of forces later. But that means that they're all either coming in, they're either pointing into the board or coming out of the board as a vector. To make it a little clearer, we'll say that they're either clockwise or counterclockwise. Okay, we don't have any torques causing the block to flop over about an x-axis or something. They're all being twisted about point P, which we can consider to be the z-axis going in and out of the board. Okay, now notice that the friction force and the normal force both act through point P, and so the distance to their line of action is 0. So they exert no torque whatsoever about point P. And so the only forces that do exert a torque are the pulling force and the gravitational force. Those are the forces that will exert a torque. And so now we'll take a look at our equations. We look at the pulling force. It tends to rotate it in the clockwise direction, which we're going to say is negative. Find that as negative. And so we have minus the pulling force times d1. Okay. That's a torque going, let's see, into the board. The gravitational force, which we'll just say, call that the force of gravity, Fg times d2, that's a force that's counterclockwise, so it's a force pointing out of the board. Okay, so we'll add those up, and they have to add up to be 0. Okay, and so now we'll substitute what we know for the pulling force, which is equal to U times mg, plus the gravitational force is mg, d2, oops, see, I forgot to put in the d1. Okay, this is times d1. Okay, that's the torque, that's this torque right here, plus the force of gravity, which is mg times d2, and it has to be 0. Notice that we have mg in both terms, and so we can calculate our distance. I'm sorry, I want distance d1. That's what we're trying to find. Trying to find d1. So we calculate d1 to be equal to d2 divided by u. Okay. And so now what we've done is we've done a problem in static equilibrium by simply knowing the definition of torque and by understanding that the torque caused by a force is equal to the force times the perpendicular distance to the line of action of where the force is applied about a pivot point. Okay, in subsequent video, we'll talk about what if the force is at some kind of an angle. What could be a general representation? We know that it's not always going to be perpendicular to the floor or parallel to the floor. Supposing it was at an angle to the floor. That makes our life a little bit more complicated, and we'll learn how to deal with that next time.